previously we have solved few problems that involve the fraction. Okay, all you need to do is to manipulate the expression so that you have term that is similar to what you have in the table. Okay, the mapping process. But somehow in a certain problem, you were given a fraction where the denominator is a quadratic expression. Okay, for example, in this case here, okay, is given here 3s plus 1 over s squared minus s minus 6. Okay, so we don't have this kind of expression in the table. Okay, and all the manipulation that we have seen before, okay, is not applicable here. Okay, so the idea is to rewrite the quadratic expression here. Okay, so I'm going to put it like this. You are given a fraction with a quadratic denominator. Okay, so you need to check the denominator, okay, and see whether the denominator can be factorized into bracket times bracket. Okay, so if it is possible, then you do partial fraction. If it is not possible to rewrite the denominator in the bracket times bracket form, then you do the completing the square. Okay, so this is the approach when dealing with the inverse Laplace transform when it comes to a fraction with quadratic denominator. Okay, so for example, if you're given the fraction 3s plus 1, this is what you have in your lecture notes, s squared minus s minus 6. Okay, so first of all, you need to check this denominator. Okay, is it possible to write in this form? Okay, so we can see that this is actually s plus 2 s minus 3. So this is possible. If this is possible, then we perform the next step is to perform the partial fraction. Okay, so we don't do the completing the square. So in other example, so let's say the fraction that you have is this 2s minus 3 over s squared plus 2s plus 17. So this one, okay, you cannot factorize into bracket times bracket. So this denominator here, okay, this is not possible. So it means you need to do the completing the square in order to find the inverse Laplace transform. Okay, so we'll see few examples, okay, that use this approach and also this approach. The first approach is by using the partial fraction. Okay, so if you can see here, okay, these are the type of denominator that you should know in partial fraction. So I hope you can recall what you have before in Engineering Maths 1. Okay, you have solved the integration by using the partial fraction. So you are going to apply that technique. Okay, one more time here. It's just that before this, you are dealing with the x variable. So in the inverse Laplace transform, we are dealing with the s. Okay, so don't get confused with the s and x. So they are basically the same technique here. Okay, the partial fraction decomposition. Okay. Okay, so I hope okay you are familiar okay about this partial fraction. I'm not going to start from scratch. Okay, we are just going to apply it. Okay, so if you cannot understand this, okay, please ask around, Google around. Okay, if you still cannot get what is the partial fraction all about, then maybe you can contact me personally. Okay, so now we are going to see the idea of why we perform, or why do we need the partial fraction in inverse Laplace transform. Okay. Okay, so take the example here. We have this fraction with a quadratic denominator. Okay, so this term, okay, in none of the term that we have in the table, okay, is similar to this form. But somehow, okay, if we can rewrite this in terms of partial fraction, so it means that, okay, this example here in terms of partial fraction, okay, can be written in this form. Okay, so the process that you have to go through is basically this one in this box here. Okay, um, so the original term that you have here, okay, is equivalent to these two fractions. Okay, so it means finding the inverse to the original expression here is equal to the finding the inverse to these two new terms, but they are actually equivalent. Okay, so we are not changing anything. Okay, they are just equivalent. So we can see that this form, okay, is something that we have in the table of Laplace. Okay, so if we can recall, we have the fraction, this one, 1 over s minus a. So even though we have 1 over s plus a, this just simply means s minus negative a. Okay, so that's why, okay, we want to rewrite the fraction that we have, okay, in terms of partial fraction, because we know by doing that, we can now map to our table. All right. And then it'll be just a straightforward solution. Okay, so for example, this one can be written in this form. Then the inverse to 1 over s plus 2 is simply exponent negative 2t. And then the inverse to the 2 over s minus 3, so you can take 2 to be in front. And then the inverse to the 1 over s minus 3 is simply exponent 3t. So that's it. Okay. And now, okay, tips when dealing with the fraction I've mentioned, okay, earlier. Okay, if the denominator can be factorized in terms of bracket times bracket, then you do the partial fraction. Otherwise, you do the completing the square. Okay, so let's see example 19 here. Okay. So you are given the inverse to the 5s plus 1 over s squared minus s minus 12. Okay, so you can see the fraction is quadratic. Okay, so you need to check whether this can be written in the form of bracket times bracket. If it is possible, then proceed with the partial fraction. Otherwise, do the completing the square. Okay, so if we take out 5s plus 1 over s squared minus s minus 12, then we know at the denominator we can write in the form of s plus 3 s minus 4, meaning that it is possible to factor out in the form of bracket times bracket. So at the top, okay, it is maintained to be 5s plus 1. Okay, so by the partial fraction decomposition, we have linear factor. S plus 3 is linear, S minus 4 is also linear. Then we know it should be written in the form of A over s plus 3 plus b over s minus 4. Okay, and then 5s plus 1 is equal a s minus 4 plus b s plus 3. Okay, so cut the story short. Okay, I just assume you know how to get the a and b. So in this case, a is supposed to be 2, b supposed to be 3. Okay, so please make sure you get the value of a and b. Okay. Um, so now the inverse that we want to find 5s plus 1 over s squared minus s minus 12 now is equivalent to the inverse of a, which is 2, over s plus 3, okay, plus the inverse to the b, which is 3, over s minus 4. Okay, so it is simply 2 times. Okay, so inverse of 1 over s plus 3 is just exponent negative 3t plus 3 times exponent of 4t. Sorry, negative, positive 4t. Alright, so that's it. Okay, so that's how we use the partial fraction in order to get the inverse. Example 20, we have 4s squared minus 5s plus 6 over s plus 1 s squared plus 1. So this is already been given in the form of bracket times bracket. So we know that straight away we need to do the partial fraction. So we have the linear factor s plus 1. So it need to be in the form of a over s plus 1. But the second term here is quadratic. So when you have quadratic factor, then it should be in this form at the top, bs plus c, okay, over s squared plus 4. Okay, so be careful. Okay, this is actually the common mistake. Okay, so normally students tend to write b over s squared plus 4. Okay, so since this is quadratic, so at the top it should be bs plus c. Okay, so by the partial fraction decomposition, okay, cut the story short here. So I just put a, b, and c value. Okay, make sure you get these values, 3, 1, and negative 6. All right, so it means what we want to get, the inverse to the all of those just in the bracket. So I'm going to just write this one. So this is the term is equal to or equivalent to the inverse of a, which is 3 over s plus 1. Okay, and then we have the inverse to the bs, so b is 1, so we have s, c is negative 6, so minus 6 over s squared plus 4, which can be written further in the form of, you can separate the second term here to be in 2, okay, individual fraction. Okay, so we have here for the first term, this is straightforward 3 exponent of negative t, but for this one, the second term can be written in this form, s over s squared plus 4 plus the inverse of 6 over s squared plus 4. In fact, this is minus. Okay, because we have negative 6. And then, okay, this is simply, if we refer to the table, s over s squared plus 4 is simply cos 2t. Okay, and this one is, so we can write this one to be s squared plus 2 squared. So at the top it should be 2, then we need to multiply with the 3. So we have minus 3, and that one is the sign, sine 2t. So that's it. Now, the second approach is by using the completing the square. Okay, so this is, so you use this when you cannot factor out your quadratic expression in the form of bracket times bracket. Okay, then you do the completing the square. So completing the square means we want to transform the quadratic expression ax squared plus bx plus c to be in this form. A in the bracket we have x minus h square plus k. Okay, I don't know, maybe before this you have the formula for the h equals negative b over 2a something, okay, and then k is c minus whatever, okay, whatever formula that you have learned before. Okay, I cannot recall that one, but if you comfortable with the formula that you have learned before, then just proceed. Okay, as long as you know how to do the complete and the square, then it should be fine. Okay, but my technique is very simple. For example, if you have s square plus 4s minus 3, for example. Okay, so this one cannot be written in the form of bracket times bracket. Okay, so we need to do the completing the square. Okay, so it means we want to write in this form. Okay, plus somewhere here plus or minus with the something. Okay, so what we need to look for is the coefficient of s, including the sign, whether it is positive or negative. Okay, so the positive 4 here, you divide by 2. So you have 2, right? So it is simply s plus 2. Okay, so you have here the result of 4 divided by 2 is 2. Okay, so you have that one. And then this value that you have here, okay, you need to square this value. So you have 4, right? So keep 4 in your mind and think of what do you need to do with the 4 so that you get the negative 3 here. So you have 4 in your head. In order to get the negative 3, okay, so you need to have minus 7. Okay, so that's your completing the square. Okay, so if you want to check, then you need to expand the bracket. Okay, so you have s squared plus 4s plus 4, but you have minus 7, then you get negative 3. Negative 3. So this is the completing the square form of s squared plus 4s minus 3. Okay, take another example. If we have s squared minus 6s plus 8, for example. Okay, in terms of completing the square, so we want to write in this form. So we look at the coefficient of s, which is negative 6 here. You divide it by 2. So you get negative 3. Okay, so negative 3 means you have minus 3 here. And then this negative 3 here, you need to square this value. So you have 9. What do you need to do to the 9 so that you have positive 8? Okay, so you have 9 in your head. So you need to minus with 1 so that you have 8. Okay, so if we expand, then we have s squared minus 6s plus 9 minus 1, which is 8. So this is the completing the square to the s squared minus 6s plus 8. Okay, so I hope you really understand the completing the square technique. Right. So next we are going to see how do we use this in finding the inverse Laplace transform. Okay, look at example 21. Okay, so we have the fraction with the denominator that involve the quadratic expression. So s squared plus 2s plus 17 cannot be written in the form of bracket times bracket. Okay, so we do the completing the square. Okay, so now the question is, why do we need the completing the square? Okay, in solving this problem. Okay, so if we do the completing the square, meaning that the fraction, okay, can be written in this form, okay, plus or minus with something here. Okay, so somewhere here is s plus or minus something. Okay, so if we can rewrite the expression that we have here to be in this form, then we can map to the table. Okay, so if after we have written in this form, okay, so we can see this is something that we have done in a previous discussion. Okay, so it will be something like this one, example 18. When you have written your denominator, okay, by the completing the square, so you have something like this. Then you know that this form now can be mapped to the fs minus a. The same thing here. Okay, when you have the completing the square, meaning that you have something in this form, bracket, okay, square. Then you map to the fs minus a. Okay, so this is the form of completing the square. Okay, so that's why that is the idea of why do we perform the completing the square. Okay, so that we have term that is similar to what we have in the table. Okay, so go back to this example. Okay, so first of all, s squared plus 2s plus 17 cannot be written in the form of bracket times bracket form. Okay, so therefore do the completing the square. Okay, i.e. s squared plus 2s plus 17 equals, okay, so in completing the square form, you have that. So look at the coefficient of s, which is 2. You divide by 2, so you have positive 1. So s plus 1 squared. 1 square is 1. Okay, so in order to get the 17, so we need to add with 16. So this is your completing the square form to the s squared plus 2s plus 17. So it means that the expression that you want to get, okay, so assuming this is the star term, is now equal to the inverse to the 2s minus 3 over, so you write your completing the square form, s plus 1 squared plus 16. Okay, which can be mapped to the inverse to the fs minus a. Okay, because in the bracket here, we have a function in the form of s minus something, basically by looking at your denominator here. So you know that your a is negative 1 if you map this one to this one. Okay, but we need to be very careful here, because at the numerator here, our s here is not yet written in the form of s minus a. So if the denominator is s plus 1, then at the numerator, it should be in the form of s plus 1 as well. Only then we can completely mapping to this one. Okay, so it means that we need to perform a little bit of manipulation to the 2s minus 3. Okay, so therefore, the inverse to the 2s minus 3 over s plus 1 square plus 16 is now equivalent to, okay, so let's see now, how do we manipulate 2s? So we want to have s plus 1. So at the denominator, we have s plus 1 square plus 16. So at the numerator, we put s plus 1. but we already changed the original expression. The original term is 2s minus 3, but so far what we have here is 2s plus 2 if we expand. So in order to get minus 3, so we need to subtract with 5. So if we expand, then we have 2s plus 2 minus 5, which is negative 3 at the left. Okay, so this is now f completely, exactly f s minus a, which is f s minus negative 1. Okay, so by that we know that our a equals negative 1 and our f s minus negative 1 or s plus 1 is equal to 2s plus 1 minus 5 over s plus 1 square plus 16. Okay, so by the table, the answer to this should be in the form of exponent ATFT. So your task is actually to get what is this FT. So FT comes from the Laplace or the inverse to the Fs. Okay, so we need to get what is our Fs, and then we take the inverse to that. Okay, so since we have Fs plus 1, so therefore Fs only, meaning that we remove positive 1 at the left. Okay, we also remove positive 1 at the right, so we have 2s minus 5 over s squared plus 16. Okay, so therefore ft that we wish to get is the inverse to the fs, which is inverse to the 2s. Okay, I separately written in two individual fractions. So this is 2s over s squared plus 16 minus the inverse to the 5 over s squared plus 16. So now if we map to the table, okay, so these two here can be put aside. So in the bracket, we have s over s squared plus 16. So the 16 is actually 4 squared. Then by the table, it is straight away the cos. Okay, let us written for this one first. So by the table, we know this one should be written in the form of 4 squared. So at the top, it should be 4. So in order to get back this 5, then we need to multiply with the 5 over 4. So by the table, this is 2 cos 4t minus 5 over 4 can be put aside. So in the bracket, we have inverse 4 over s squared plus 4 squared, which is sine 4t. Okay, but don't forget, our answer should be in this form. Okay, so at the end, our answer is supposed to be the inverse to the original term that we want to get is equal to the exponent at. Our a is negative 1 at the first place, so exponent negative at times 2 cos 4t minus 5 over 4 sine 4t. That's it.